All right, our next up presentation is Luis Campos of the European Space Agency, presenting on flight software in ESA's Euclid mission. And I believe we have his slides to bring up and get going. Thanks.
Hello, and thank you for joining today's presentation. I'm Luis Campos, and I'm the Software Operation Engineer in ESA's Euclid project. Today, I will be describing the overall software running in ESA's Euclid mission. A quick overview of this presentation. I will present the Euclid mission and objectives. I will follow by presenting the overall spacecraft avionics and where each software is running. Then, I'll do a brief description of each software. Finally, I would like to present some unique features that are on board of Euclid. So, what is Euclid? Euclid is a space telescope that aims at measuring and characterizing dark matter and dark energy. A brief time description of our universe life. Our universe started around 13.7 billion years ago with the Big Bang. However, we can only really see what happened in the universe from the moment the matter decoupled from light. This was about 380,000 years after the Big Bang. The first light that was emitted in the visible spectrum, it is still visible to us as a redshift, and it's called microwave cosmic background. A dark age followed this first light until the first stars were born, about 400 million years after the Big Bang. Euclid will start observing when the stars and galaxies formation was peaking. That's about 10 billion years ago. Ever since the Big Bang, our universe has been expanding. This expansion is actually accelerating, meaning planets, stars, all matter in the universe is getting faster and faster. The cause for this is not yet truly known, and the cause of this acceleration is what is called dark energy. Dark in the sense we cannot directly measure it. In parallel with the matter that exists in the universe, there is dark matter. Again, dark in the sense we cannot directly measure it, but we can measure its effects. For example, by seeing a light beam bend as it passes by a big mass, such as a galaxy, which you can see, or a big concentration of dark matter, which we can't. Euclid telescope will look at very far away galaxies, not only track their movement for the 6-year mission, but also detect the shape of the galaxy and if it is distorted. This will provide key information to characterize both dark matter and dark energy. In order to do this, Euclid will do a step and stare, meaning point to a galaxy and look at it for more than 560 seconds, which is more than 9 minutes, and will do this for about 36% of the sky. Now, I would like to present you in more detail the Euclid spacecraft. The spacecraft can be mostly divided in two main components, the platform and the payload. The platform is responsible for the attitude and orbit control, propulsion control, data handling, communication with ground via both X-band and K-band antennas, power, thermal control, and of course FDAR. Therefore, the platform manages all core functionality of the satellite that allows it to work. The payload module is therefore responsible for managing all scientific instruments. At its core, it's a large 3-mirror telescope that feeds light to two instruments, the VIS and the NISP. The VIS, short for Visible Imager Instrument, is able to perform exposures in the visual spectrum of light, while the NISP, short for Near Infrared Spectral Photometer, is able to perform exposures in the near infrared spectrum of light. A key feature of Euclid is that both instruments can perform these exposures in parallel, providing data that can be correlated between both instruments. In order to have a sharp image, the secondary mirror, called M2, is assembled on a mechanism, the M2M, which allows a 3-degree of freedom adjustment. This is used to compensate for any movement from launch or the cool-down period due to thermomechanical movements. The M2M is so precise that it is able to control the movement of the M2 with a 0.1 micrometer precision. Finally, I would like to show you the full Euclid Avionics and show you where flight softwares are run. The platform software, illustrated in red boxes, are embedded in multiple equipment, namely the fine guiding sensor, the mass memory unit, the control and data management unit, the star tracker, and the micropropulsion electronics, which controls the micropropulsion system, while the payload software, illustrated in green boxes, are embedded in the two payload equipments, the VIS and the NISP. Having shown you the overall Euclid's architecture, I want to dig deeper and showcase each software running in it. And I'll start with the mass memory unit software. A quick overview of the mass memory unit itself. The MMU is responsible for collecting, storing, and forwarding to ground the data generated by all platform and payload equipments throughout the mission. It collects data in its 4 terabit NAND-based flash. The MMU is controlled by the CDMU via MIL standard 1553 bus using the CCSDS POS standard. It is composed by 4 main boards: the memory system supervisor, where the main computer is and where the software runs, the flash memory, where the data is stored, the input module that collects data directly from the payload instruments via dedicated spacewire link, and the output module, which is responsible for sending data to ground via the K-band antenna. The MMU contains 2 softwares: the boot software, responsible for startup of the hardware, the MMU application software, which is the main software performing all required features. The MMU software runs on ERC32. It has 4 megabytes of RAM and it's stored in a 1 megabyte EEPROM bank, which allows to be patched in flight. The boot software is stored in a 64 kilobyte EEPROM. The MMU application is built in a classical layer approach, where hardware and operating systems are hidden from higher levels. The middle layer manages the flow of data exchange, while the 2 top applications handle the file delivery and the file storage. The MMU software is a mix of new software, namely the top applications, and heritage flight-proven software like the data handling system or the qualified RTEMS operating system. A key feature of the MMU software is that it supports the operational concept of using files as means of transferring data both uplink and downlink. This is called file-based operations. For that, the MMU software manages Euclid's file system with 1 level of directory, means not directly inside of directories, but multiple parallel directories can coexist, and of course, several files inside each directory. Since the storage technology used is the NAND-based flash, the MMU software is also responsible for managing the constraints coming from that technology, such as bad blocks, erase block before write, or wear leveling. This is achieved by defining a logical memory area, and that can be split from the actual physical memory, and therefore contiguous local memory areas are not necessarily contiguous in physical memory. Finally, the MMU software is able to forward data directly to ground. This is done using the CCSDS CFDP protocol. In Euclid, we can transmit up to 6 files in parallel to ground. The Fine Guiding Sensor FGS is a novel equipment running purposely built software. The aim is to provide very accurate measures of the spacecraft position and/or velocity. It is crucial as Euclid needs to be very still during VIS or NISP exposures, and any micro disturbance needs to be corrected by the micro propulsion system. The FGS itself is split between a cold site located near VIS, composed by CCDs and data collecting hardware, and a hot site located in a platform site composed by a cold redundant onboard computer where the software is running. The FGS software is composed by 2 softwares. The startup software, stored in bootprom, is responsible for booting up the FGS and loading the main software, and the FGS application software. The application software is a newly built software that manages all FGS main system modes, including FDAR fallback modes. It is built in a layered approach where the hardware interfaces are hidden from application level. The application software also manages communication with the CDMU via the MIL standard 1553 bus using the CCSDS bus standard. The application software has 2 major modes: the relative tracking mode, RTM, where every 2 seconds a new velocity and relative position is calculated, and the absolute tracking mode, ATM, where the position is known as it's matched against a star catalog. This star catalog is a set of files uploaded by ground that work in a very similar way as Star Tracker does. All the management of uploading the correct file in the FGS is in charge of the onboard software running in the CDMU. The onboard software running on the main computer, the CDMU, is at the heart of the full system control, including FDAR, and it plays a key role in the success of Euclid mission. Without the functional onboard software, the mission is not possible. 2 softwares are part of the CDMU. The boot software is responsible for starting up the hardware and passing the control to the main software if we are on the master processor, or managing memory requests if we are running the redundant processor. Then the onboard software is the main software. This is composed by three components: the Central Application Software, CAS, the OSS Application Software, AS, and the High Gain Antenna Software. These three components are coded independently and rely on the module design of the CAS to be integrated when building the flight onboard software. The software runs on a Leon 2 running at 64 MHz. It has a 60 MB of SD-RAM and it's stored in an 8 MB EEPROM, while the boot software is stored in a 64 KB PROM. I will now present in more detail the three main components of the onboard software, starting by the Central Application Software. The CAS is the main software component as it provides the backbone for high-level application. Some of these applications are contained in the CAS itself, but some are not. The CAS has a layered software architecture where both hardware interfaces and the operating system are wrapped. The data handling layer provides the core services implementing most of the CCSDS bus services, such as housekeeping, monitoring, mission timeline, and OBCPs. This layer is inherited from other past projects, providing a flight-proven software framework. On top, the CAS implements one application for each system functionality, such thermal control, propulsion, communication, system mode management, or payload management. And finally, the CAS also performs the system FDAR management. This is done in the System Safeguard Layer, SSL, and it implements a 4-level design where a failure is detected and, if possible, corrected at the lowest level. Taking advantage of the layer architecture of the CAS, the software component controlling the high-gain antenna is built externally and linked to the CAS to build the full flight onboard software. The purpose of the high-gain antenna software is to control the steering, azimuth, and elevation of the high-gain antenna such that ground station positions are targeted for data download. This enables a high-speed downlink rate to be possible. The high-gain antenna software manages its own state machine. The high-gain antenna software has its own task whose schedule is fully controlled by the CAS and interfaces the CAS via a dedicated software interface. As an external equipment, high-gain antenna is commanded via CCSDS bus service 8 TCs that are forwarded by the CAS data handling system towards the high-gain antenna software task. The OCS software is the third and final software component composing the onboard software. The OCS software is responsible for the orchestration of the full OCS system. That means managing the spacecraft attitude, managing the multiple OCS modes, and also collecting data via the CAS of all OCS units, processing that data, and issue commands such that Euclid pointing is undisturbed. Finally, the OCS software is also responsible for managing the FDAIR, namely related to spacecraft safe attitude. An interesting feature of Euclid OCS system is that unlike other spacecraft, Euclid uses a no-spin reaction wheel approach when performing exposures in science mode. This implies a start-stop approach of all reaction wheels in the spacecraft. The OCS software itself is a single task whose schedule is controlled by the CAS. The communication with the CAS is done via a dedicated software interface. The OCS software architecture is composed by two subcomponents: a manual code, which contains the functionality to interface the CAS, and also a set of basic core mathematical functions. It is also the wrapper for all functionalities provided by the auto-generated code. The auto-coded component, which contains the functionality for the guidance, navigation, and control of all OCS modes except the safe mode. The safe mode is coded in a classical way. The Euclid autocode software is generated from MATLAB models using well-defined autocoding rules. The produced code is nevertheless validated in high-level testing as standard code. The manual to auto software interface approach is based on the autocode providing standalone functionalities, which is later on called by the manual part. Having described all platform softwares, I would like to provide a brief description of the softwares running in the payload instrument. The VIS equipment is responsible for exposures in the visual spectrum and at its core is controlled by the VIS software. The VIS software is split in two main components: the boot software, responsible for starting up the VIS instrument and loading the VIS application software, and the VIS application software The main software responsible for managing the VIS mode, communication with the onboard software via the MIL standard 1553 bus, collecting, compressing, and transferring to the MMU via SpaceWire link all the scientific data. The VIS application software uses the CCSDS lossless data compression 1-to-1 as its compression algorithm. The NISP instrument is responsible for performing near-infrared exposures. As per other equipment, a boot software is present in the ICU board that is responsible for starting up the hardware and loading the ICU software. The NISP ICU software is the main software responsible for handling the communication with the CDMU. It manages also the interface with the DPU and loads the NISP DPU software. The NISP DPU software is responsible for the collection of scientific data and further transmission to the MMU. Prior to the transmission, data is compressed using the CFDP library. Now I would like to present you some special features implemented by software in Euclid mission. Euclid file-based operation concept is supported by the CCSDS File Delivery Protocol, CFDP. This protocol is used both for uplink and downlink of files directly to, from, the mass memory unit. Euclid uses different CFDP classes for upload and download. For upload, it uses class 1, that is unacknowledged transfer, which implies that uploaded files can be lost. This is mitigated by always uploading files several days before being needed. For download, it uses class 2, that is acknowledged transfer. Therefore, downlink data is not lost and hence science data is not lost. The deletion of files is only done when the files are correctly on ground. The full CFDP protocol is implemented both in space and on ground. For that, 3 CFDP entities are defined in Euclid. One, on board in the mass memory unit, implemented by the mass memory unit software and hardware. A second, in the CFDP assembly, located at the currently used ground station so that it is able to react fast. And the third one, the mission control system, located at the mission operating center, which is responsible for closing the loop and receiving the files. The Euclid spacecraft uses a port of the MicroPython engine as the core implementation of the CCSDS Bus Service 18 managing OBCPs. MicroPython is an optimized implementation of Python 3 to run on microcontrollers and in a constrained environment. MicroPython component is built in 2 elements, a MicroPython virtual machine and the OBCP engine that together are the software application executing the onboard control procedure in MicroPython language. And the MicroPython STE, an editor, the cross-compiler, is responsible for generating the MicroPython scripts to be later uploaded towards the MMU using the CFDP protocol. The MicroPython interpreter in Euclid has some special features. For example, it is able to run parallel OBCPs with different priorities. In Euclid, the system is configured to have 1 high priority OBCP and 10 normal priorities OBCPs. Each OBCP script is effectively run as an independent RTEM task that holds 1 virtual machine. High priority OBCPs are associated to high priority tasks than the normal OBCPs. Between tasks with the same priority, a round-robin schedule is performed with executing time slices, a feature of RTEMs. This avoids, to some extent, a starvation and allows all OBCPs to run over time. In order to avoid any impact to other applications, MicroPython tasks are defined as the lowest priority in the system. This implies that no critical bound function is to be performed using OBCPs as time is not guaranteed. The MicroPython OBCP also allows to perform time synchronization, either by simple sleeps or waiting until the next rise of the system clock. Finally, another interesting point of this MicroPython engine is that it had to change the floating point trap handler, such that if an exception comes from the OBCP, the trap does not impact the external system. However, the OBCP itself, it stopped. And this is a simple example of an OBCP building a sequence of TCs to request a memory dump via service 6 to a specific equipment. In tests performed in Euclid running all 11 OBCPs in parallel, an average CPU load of 2.5% is measured in real time. So, at conclusion, Euclid mission is a complex scientific system with many interfaces and software running in parallel. The onboard software plays a key role in the success of the mission, as it is also the main FDAR component. In Euclid mission, most softwares are purposely built, but there is a strong heritage from past projects. Innovative features as file-based operations anchored in CFDP protocol or MicroPython engines for the OBCP pushes forward the functionality of Euclid. I would like to acknowledge the instrumental role of some people to the Euclid software, namely David Sanchez for his work in MicroPython, Thanasis Tsiodras for his support in many softwares of Euclid, both in platform and payload, and of course Cyril Colombo for his role in setting up the initial design of multiple software. Finally, and because it's impossible to name them all, a thank you note to all industry team members that work on Euclid software.
All right, thank you, Luis. We got a few minutes left for some questions, and a couple of them are coming in already. So the first one from Timothy Cannon. How did you handle dynamic memory on MicroPython, such as heap, fragmentation, and garbage collection after initialization?
We don't. We actually lock it. So that is part of one of the adaptations that we did also, and this also is a little bit the feature of this MicroPython. So this is really targeted at microsystems.
Okay. Next question from David Horn. What boot software is used across all of these platforms?
It really depends on the supplier, usually on the hardware supplier. So for example, the one that we are using for the main computer is from RUAG, and that is provided by them. So it really depends. All of them are, of course, Cat B, so they really can't fail, but it depends on the supplier. So we don't have one boot spread it all. So FGS has another one, and it depends on the software and the hardware.
Oh, okay. Next question from Alan Cudmore. Are multiple copies of the flight software maintained on board, and can new versions be uploaded in flight?
Yes, so you tend to have about 4 different versions depending on, so 2 per PM, so processing module, and with two in each processing model that is also redundant, so you have 4. And yes, you can upload flights directly, so in patching. There are multiple ways of doing it, either in patch or full upload of an image.
Okay. Next question from Chris. What was the hardest challenge of using MicroPython?
The VM, the integration, because of course we need to have it integrated with the hardware. So that was a bit the hardest, although this work was a little bit on the side of Euclid. Euclid just got a lot of benefit from work done on the side by David for tech, and also how you configure it.
Okay. And next question, why was FGS not included in the AOCS sensors?
Clearly by mistake. So actually FGS is the main, I don't know, but it is actually the main sensor sort of Euclid for when he's doing science. Is let's say a glorified star tracker. Is a very, very, very precise star tracker, let's say, put it simply like that.
Okay. Next question, also from Chris. How are files used in commanding? Can the same files be used on the ground and in flight for testing?
Yes. So files is really the base of what we have. So you have either OBCP files, or you can have files that are TC files. So most of the commanding are actually done on MTL, so mission timeline. So basically a list of TCs, and we don't really have in Euclid. There are other projects that have a file to MTL load. So that doesn't exist in Euclid. But you can, all the files that are uploaded are tested on ground, for sure.
Great. Thank you so much, Luis. I think that's all the time that we have for questions today. Thank you so much for your time. Have a good evening.
Thank you very much. Bye.
Yep.